now we are recording. All right, so data structures in Grasshopper. Let's begin. So I'm going to show you this on a Photoshop window rather than, wait, god damn it. Now my tablet is freaking out, of course. It's always something. It's always something. Okay, mapping on. Okay, now it's fine. So I'm going to show you this on a Photoshop window rather than Rhino, simply because it's easier to follow along if I just draw it rather than showing it. Why are you doing that? Yeah, okay, so now it works. So let's see, and every time when I screw it, we'll do it this way with mouse. Yeah, cancel. We'll do it this way with mouse. So you are used to lists at this point, right? So a list is just basically a set of things, right? It can be numbers, it can be meshes, it can be B-reps, polysurfaces, doesn't matter, but it's basically just a list of, of things, right? And that list has numbering, like 1, 2, oh my beautiful writing, 1, 2, 3, 4, and so on. Actually, it doesn't have that. It starts from 0, so it's rather 0, 1, 2, 3, and so on, right? Which messes with your head a little bit. Since all of the lists and everything, all of the counting in Grasshopper is done from 0, but it is what it is, right? So we have a list of, when it's just a list, we have just, a set of values or a set of meshes, and that's easy to understand. But when we have a, can I make this bigger? Just brush over it real quick. But when we have a data structure, it's basically like, it's wrong to say it like that, but it's basically a list of lists, right? So imagine it being this way, and I had an example that I wanted to draw, but I can't draw it. So instead, what we're going to do is we're going to say container. Let me find the image of a container. Not a container. Let's do a bucket. Yeah, that's perfect. Okay, so let's say we have a set of buckets, which is a nice one. Let's say this one. Copy image. Where's my Photoshop? Paste it here. Okay, so we have one bucket. Transform it to make it smaller. Like that. And then another bucket. And the third bucket. Let's say we have 3 buckets, right? And in each of those buckets, we have, I don't know what, we have ducks, right? I would prefer to have a duck with, yeah, sure, rubber ducks. That's fine. Copy image from there and paste it here. Can we multiply the duck? Yeah, we can. Okay. So we have 1 duck. Let's say we have 2. And we have 3 ducks here, right? And let's merge the layers and just copy and copy. So we have, let me just merge the layers real fast and multiply this. Okay, so we have 3 buckets with 3 ducks in each bucket. And let's say each duck has some sort of a, I will not be copying any images, but let's say each duck has 2 freckles on its cheek, something like that. Like just 2 dots. And why can't I, hello? Why am I struggling with freaking Photoshop? Oh yeah, because color picker is in the wrong screen. That's cool. So freckles, and let's make them smaller, even smaller. Poke, 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 poke. Just two dots on each duck. Maybe I should have chosen a different color, but you get the point, right? So now, if we were to talk about precisely, let's say, this freckle right here, we need to somehow instruct Grasshopper as to which freckle we're talking about, right? So we need to guide the Grasshopper to understand that it's precisely that freckle that we're talking about. And this is where data trees come in. So let me kind of come back a little bit and showcase it this way. So this is bucket number 1. Beautiful. This is bucket number 2. And this is bucket number 3, right? This is duck number 1, 2, 3. That's not a 3, but you get what I mean. 1, 2, 3. 1, 2, 3. And then if I were to zoom in and start naming the freckles, it would be freckle number 1. Oh, that's a very thick one. Let me make this thinner. Freckle number 1, freckle number 2, freckle number 1, freckle number 2, right? So this freckle in particular would be freckle number 1, right? And this one would be freckle number 2. So now, how do I describe precisely? Let me change the color real quick. How do I describe precisely this freckle in Grasshopper, right? Well, I say it belongs to bucket number 2, right? So it's within bucket number 2. And it's on the duck number 2, right? And it's freckle number 1, right? So this is an address of a data tree. If I were to draw the data tree itself, and we'll come back to this to flesh it out. I will do the same thing in Grasshopper. But if I were to draw the data tree of the image that I made here, it would look like this. So we would have, some sort of a starting point for the data tree. Let me zoom in here. Starting point. And then we have bucket number 1, bucket number 2, bucket number 3, right? And then from each bucket, it would be duck number 1, duck number 2, duck number 3. 1, 2, 3. 1, 2, 3, right? And then in each, for each duck, there would be freckle 1, freckle 2, freckle 1, freckle 2, freckle 1, freckle 2, freckle 1, 2, 1, 2, 1, 2, should have made less ducks, but what can you do? Okay, so that's how the data tree would look like, right? So now when I say that the address is 221, right, of the data tree, I know that I need to start, of course, we start from the beginning, and we say 2, right? So this is branch number 1, this is branch number 2, right? So we go through to this branch, then we arrive at this point, and then I check it again. It says 2 again, right? So we continue onto this branch here, and then it says 1, which means it's this branch right here. So that freckle, this freckle right here, rests right here, right at this spot. And this is basically how any kind of a data tree structure behaves in Grasshopper, right? You have an address, you have a data tree, and you have addresses for every branch. Also, I made a mistake during this tutorial, and that mistake was that I counted from 1. As everything in Grasshopper, you start counting from 0, right? So it's actually bucket number 0, bucket number 1, and then bucket number 2, rather than 1, 2, 3, it's 0, 1, 2, right? Which, yeah, again, it messes with your head, but it is what it is. Let me do the same thing in Rhino, and I already have it here. So let me turn on Grasshopper. Let me just run it real fast, and we'll see what we get. Come on. How much RAM am I using? I think I'm going to crash my... Yeah, yikes. That's 15 gigabytes. We'll see. If it crashes, we'll just start the Zoom meeting again. So if the whole stream crashes, check your emails because I will be sending out a new Zoom link to you. But it seems to be a little bit unstable right now. Hello, why are you so big? Okay, you're small again. All right, so Grasshopper. Let me just, here in the top, let me create 3, in the top view, let me create 3 circles. 1, 2, 3, doesn't matter. Let's say they're the same size, that doesn't matter. It's 3 types of geometries, and these circles are our buckets, right? So I will type in CRV into Grasshopper, right-click on it, set multiple curves, and now these 3 circles are inside of Grasshopper, and if I were to check it with a panel, I would see that, you know, I have a list of 3 items, 0, 1, and 2, right? My 3 buckets. Then, let's say in each of these 3 buckets, I will randomly, not randomly, how do we do this? Well, let's do it on the edge of them. I will divide these circles, or these buckets, I'll call them circles. I'll divide these circles with divide curve tool, and I'll say that my division count is set to 2, so that I get precisely 3. Oh, that's not 3. Division count is 3, so that I get precisely 3 points, right, on each of these circles. And around these points, I will create, let's say, a polygon. Polygon. Nope, that is not the correct tool. Polygon. There we go, that is a correct tool. Polygon with, let's say, 3 segments, which is basically a triangle, right? And let's make a smaller radius. What's the radius here? Radius is 3, so let's make a radius of 2. Okay. So we have, now what we have is we have 3 buckets, and let's say inside of these 3 buckets we have 3 ducks, right? Which are represented by triangles. If I were to check the data tree structure right now with a panel, for instance, I would see that I start getting these addresses. It's not just a list anymore, but it's rather it has an address. And the address says 0, 1, and 2. If it has a bunch of zeros in front of the address, that's fine. That's just unnecessary shit that you can get rid of by right-clicking on the output and choosing Simplify. Simplify the data in this parameter by removing redundant path elements, meaning that anything that's not useful in the address is going to be removed. So if I simplify, then it's just 0, 1, 2. With 3 items in each list, okay? So right now, the data tree is not going to look very interesting. By the way, a tool that checks the data tree, how it actually looks like, is called Param Viewer, and it's located under params, under utilities, Param Viewer right here. If I connect it like so, it will say data with 3 branches, yeah, nothing special. But if I double click it, then it will show me, you know, the beginning of our data tree, or rather the actual data tree as it is right now. So right now, this only shows bucket, 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 but it doesn't show for some reason the ducks, right? It should branch out even more because we already have the ducks here, but it doesn't. And it doesn't because the ducks are not separated into separate branches. They are still, you know, they're still like lists. So, which means that every end of this branch just has 3 items rather than, you know, those items being separated. You can separate those items. You can force the ducks to have their own branch by right-clicking again on the output and choosing Graft, which is going to, yeah, what Graft does, it takes every item in the list and puts it into its own branch, right? So Graft. And now you can see we have the first branch, right? And then it immediately branches out to 3, 3, 3, and 3. And suddenly the addresses change as well, because now it becomes 0, 0, 0, 1, 0, 2, 1, 0, 1, 1, 1, 2, 2, 0, 2, 1, 2, 2. So if I come back to Photoshop, we're kind of at this stage, right? There are still no freckles, but we're at the first stage of the data tree where we have the bucket and the ducks. So let me come back to Rhino. That's the wrong Rhino. And I actually don't need to graft it right now. Every time when Grasshopper needs to create data structure, it will do that automatically within a component that you use. So if there is a component, for instance, you have 2 curves and you divide them into points, that component is going to automatically it's going to automatically create a data tree, right? It's automatically going to graft those 2 curves because that's the only way it can understand which points belong to curve A and which points belong to curve B. So here I don't really need to graft it because we are still going to make some freckles on these, on these ducks. And let's say the freckles on these ducks, let me use divide again, divide curve again on each of these ducks. And I'll say, sure, how many are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so every duck has 10 freckles, whatever. And we will say that freckles are points, right? So now if I check the data tree of the points that I'm getting, of the freckles, here, oh, maybe that's a little bit too much. Okay, let's do count of 2. It's just too long. The list is too long. So let's just say, as within our Photoshop example, they do have 2 freckles, right? So if I check it now, I can see that the data was grafted, right? But now there is a list, at the end of each branch, there's a list of 2 freckles, right? Freckle 0, freckle 1, freckle 0, freckle 1, freckle 0, freckle 1, and so on, right? But the addresses here correspond to, for instance, okay, we have 3 circles here, right? So the first number in the address is which circle it belongs to, right? Circle 0, circle 1, or circle 2. The second number in the address is to which triangle it belongs to, right? So 0, 1, or 2, 0, 1, or 2, 0, 1, or 2. And then here, since the data is not grafted, which freckle it is, you can check from the list index, right? Not from the address, but rather from the list index. To get a full-blown data tree, you could graft these points, like the output of these points, and force them to be in separate data branches. And now if I look at how the data branches look here, they're very spread out, but it's basically the same thing as I drew in Photoshop, right? You have 3 branches going on here, they branch out into 2 branches, and there are 3 main branches going out, right? So actually, let's do it this way. Print screen, that's, fuck me. Okay, print screen just almost crashed my computer. Okay, let's try again. Print screen, and let me paste it here, and let's just see. Okay, so that's the data tree, right? Okay. So if I were to draw on it, all of this belongs to the first bucket, right? All of this belongs to the second bucket, and all of this belongs to the third bucket. And then let's talk about the first bucket. All of this belongs to the first duck of the first bucket, right? And this is the first freckle on the duck, and this is the second freckle on the duck, right? So data tree is basically every time when you have more than one thing on which you apply further division, it will keep branching out these lists of lists or these data branches, just to systematize everything. Because if everything was in the same list, right, all of the freckles are in the same list, there would be no way for you to kind of walk back and understand which freckle belongs to which duck. And in doing so, you would have hard time controlling the whole script, right? Because every time when you do some sort of a division-based or addition-based function, let's say, every time you do that, you lose information because you suddenly don't know where stuff belongs, right? So that's data trees are very important, and they are by far the hardest thing, at least for me, to grasp in Grasshopper. But once you kind of grasp it, it's fine. You know, it eventually just clicks. For me, I think it was 2 years until, or 3 years until it clicked. All right. So that's that. And it applies to facades as well. So for instance, what? It applies to facades as well? I mean, let's do an example with a facade. Oh man. Rather than ducks and buckets. So let's say I have, come on, just be cooperative, Grasshopper. Just be normal. Okay. So let's say I have some sort of a surface. Let me make this a bit bigger and a bit narrower, a bit taller, and just some sort of a plane, just a surface, and maybe I will go to perspective. I will rotate it like that, rebuild it to have more, no, come on, come here, rebuild it to have more points. 4x6 seems fine. Control points on, and just kind of mess around with it, you know, to just have some sort of a change within the surface. So we have some sort of a some sort of facade element that doesn't matter, you know, the side of a building. And I will reference in this surface into Grasshopper, set one surface. There we go. Let me hide it so that we only see the Grasshopper part. And I will divide it up into panels, you know. So I will use, there's many ways of how to do it. Should we make it into a mesh? Now let's do, I don't remember how it's called. It's under utilities, Isotrim. Let's do Isotrim. So I'll just connect surface to the surface input here. It asks me for a domain. That's fine. We just go to math. And I'm not explaining what I'm doing precisely here because it's all about data trees, right? So if you need a facade creating tutorial, just YouTube it. They have many, so many different tutorials on how to create different facades. I'll just divide this domain, plug in the segments here, and sure, I'll just leave this as default. So now we have a bunch of smaller surfaces, right? Separate surfaces. And I can do, let's say, duplicate. I can first show you that it's now just a list of surfaces, and I believe it's going to be 100. Yeah, it starts counting from 0 and it ends at 99, so it's 100 surfaces. My guess is that it just divides 10 by 10 by default. And now let's say for every surface, I want to measure its center point, right? So I can get the center point by measuring an area, or rather, let's do evaluate. No, let's measure an area. So if I measure an area, it gives me a centroid of the geometry. I'm not sure if it's going to be placed directly on the surface, but we don't care about it for this particular example. And then I'm going to do some sort of a circle. That's not how you write circle. Circle around each center point. Or maybe we should do more than one. Sorry, I'm just really quickly gonna think. Maybe we should do frames instead. Let's do framing instead of adding circles. That's going to be better, I think. Maybe. Sure, let's do framing. Okay, so for these surfaces, I will just get their edges, and I'll just join up those edges into closed polylines. This is basically just an outline of each of these panels, of each of these surfaces. So naked edges, join them up, and now we can see, by the way, there is the wires that you see in Grasshopper. They also carry over information, visual information on what's going on within the wires, right? If a wire doesn't have any thickness, if it's just a black wire like so, that means it's one thing that goes through it. One number, one mesh, one letter, something one. It's not even a list, right? It's just one thing. If it's this kind of like a double wire or a thickened wire, depends on how you look at it, there are more than one thing going through it, right? So in this case, it's actually 100 segments, right? It is going through them. Here as well, right? 100 segments. If a wire is dashed, that means there is a data tree, right? It's a list of lists is going through it. And the reason why right after this node it became dashed, why a data tree was created, Because before we had just 100 surfaces, right? And after this, suddenly it becomes a data tree for some reason. The reason why it became a data tree is because for each surface, it gets 1, 2, 3, 4. It gets 4 curves, 4 edge curves, right? So suddenly it needs to know to which surface does each edge curve belong to. And if I were to check the data tree here, it will say there is 100 branches, and those 100 branches correspond to 100 surfaces, and in each branch there are 4 elements, and those elements are these curves. This, 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 and this. These 4 edge curves, right? So, after joining them, right? By the way, everything that is in a separate branch will only work, like for instance, if I join the curves and they are grouped in separate branches, right? They will only join with the curves in the same data branch, meaning that it's going to always join up into these closed rectangular curves, outlines, right? So after I join them up, it becomes still 100 branches, so it's still grafted, but now we have 1 element in each branch. If I double click on it, the data tree looks like that. It looks, you know, rough, but it's basically, let me actually simplify it. Simplify it is just 100 branches with 1 outline in each branch, right? It's the same thing as having 100 buckets, right? Instead of 3. Okay, let's move on. So let's say for each of these curves, I want to scale them down a bit to create frames. So I'll use scale on them. So I'll be scaling these curves around their center points. So again, I get the center point by measuring the area. Or not. What the? Curve must be planar for area calculation. Okay, fine. That's fair enough. We can't measure the area that way. Can we measure polygon area? How is it? It's not polygon area. Polygon center. Polygon center. Cannot convert input curve to polyline. That's cool. That's cool. Okay, so we need to get the... Oh, this is actually going to be a good example. We need to get the center points in another way, right? Not from the curves here, but rather from these surfaces. Because here I can just straight up measure area of each surface individually, and I do get those center points, right? But there's an issue, there's a problem. And that problem is that here, the data tree looks like this, right? While here, if I just check the center points, the data tree looks like that. Meaning that here, the centroids, the center points, come in as one list of 100 points, right? While here, we have 100 branches of these curves, 100 branches, but each branch just has 1 curve in it, right? So one is a list, the other one is a data tree. And how do we work with that, right? Because I wonder if this is going to crash my computer if I try to do it. Let me decrease the amount a bit, just to make sure that my computer will not crash. Let me decrease the amount, and let's try to straight up connect a list with a data tree, right? So I'll connect my centroid to the center of scaling. Yeah, that's what happens. Basically, what happens here is for every curve, for every single curve that we have, it's going to use a list of centroids, a list of points around which it scales the curve, right? Which means that every curve is going to be scaled 25 times. Because it's right now we have 25 center points. We have 25 panels, we have 25 center points. Each curve is going to be scaled 25 times, which ends up giving us 625 curves. after scaling, right? Instead of 25. So every time when you mess up the data tree structure and you connect grafted output together with non-grafted output, a list of items, it's going to square the amount of elements that you have. And it's not, that's why I decreased the amount of panels to make sure that we're not crashing the computer today. How do you fix that? Well, you can either get rid of the data tree here, right? As long as it's just, as long as it looks like that, as long as it doesn't have additional complexity, you can easily get rid of the data tree because it will just collapse into a list of curves. That's fine. Or you can create a data tree from these centroids. And we already know how to do that. The way you create a data tree is you graft the output, right? Because then it will take every center point and it's going to make a branch, a data branch for every center point in your list. So if I graft it, suddenly, right click, choose graft, suddenly it works, right? And if I were to check how both of these data trees look like, the curves and the centroids, like that, visually they seem different, right? But in reality, it's kind of the same thing, right? Because there's no additional branching whatsoever. It's just all of this crap, that the green lines and bending and so on of a data tree is redundant, unnecessary address information, which we can get rid of, just like we did here with a tool that's called Simplify. Like that. And now they are exactly the same. All right, so we have our panels, and let me mess around with the factor. Let's say 0.8. Yeah, something like, yeah, sure, 0.8 is fine. So we have our panels. Now what I want to do is actually I want to hide that, and just look at these two components here. One is the outer curve. The other one is the inner curve, right? Well, the non-scaled version and the scaled version. I want to loft them together to create a surface in between them, right? So loft, sure, I will be using loft, and it asks me for curves. I could straight up just connect them, like that, and holding down shift, connect them like that, and it will work. But my suggestion would be, especially if you are unfamiliar with data trees, my suggestion would be to, before you do that, use merge tool. And what it does, it just basically, it's the same thing as holding down the shift key and connecting many things. Only with merge, you actually know what you're connecting, what comes in first, what comes in second, right? So merge. Let me show you the data tree again of this. And it looks like it's the same thing, right? Nothing changed. The only thing that changed is now in each branch, you don't have one curve, but you have two curves, right? So merge, what it did, it said, okay, so we have two data trees with exactly the same amount of branches in both of them, so same addresses as well. So I'm going to take all of the items from data tree 1, branch 1, and I'm going to put them together with all items from data tree 2, branch 1, and merge them into one. And then from branch 2 with branch 2, branch 3 with branch 3, and so on. So the data tree still looks the same, only that it has two curves in each branch. And then I can just straight up connect it to loft, and then we have our nice panels. And then if I check the data tree here, it's kind of the same thing, 25 branches. But this time it's one element in each branch because, from two curves, it creates one loft. So you are, every time when you work with data trees, you are operating within branches as if you were working with each panel separately, and it automatically repeats the same procedure for every other panel. That's quite convenient, at least I think so. What about glazing inside, right? And this is going to be the last thing that I'll show. So let's say we do have that framework, and you can add like thickness to it and so on. We will not be doing that, but what I want to do is I want to have some sort of a glazing, some sort of a surface inside. So let me just group this. That's the frame. And here, to create the glazing, I will just choose my scaled curves, right? So the inner boundaries of my panels. These curves right here, not sure if you can see them. Yeah, you probably can see the green highlight of what I have selected. So the scaled curves, which come in as 25 different branches. And I will say explode. Explode the curves into separate segments. So as I explode them, I get the segment. I get their segments, right? And I know that it's going to be 4 segments for each, for each of these panels. So I can double check that with, again, the Param Viewer, connect segments to there, and lo and behold, it is indeed 25 branches, but 4 elements in each branch, right? It has those 4 elements. So those are 4 segments that I get. And now I can say, for instance, edge SRF, edge surface. I'll use edge surface tool, which asks me for 4 different curves from which it should build a surface, right? So it's basically asking me for 4 perimeter curves. Here, I have them in separate lists, right? But they are in lists. I can't just do this. That wouldn't work. At least I don't think it would work. Please don't work. Yeah, that doesn't work. It just kind of breaks apart, and everything is messing up. And also, it doesn't make sense to do it this way. So instead, we need to separate those 4 curves. Let me disconnect. In each branch as a separate output. And we can do that with a tool that's called list item. What list item does, it basically just takes a list, or in this case, it will take 25 lists, right? So I'll connect it like so. And by default, it will always give us the first item in the list as the output, right? So it's going to be apparently this curve segment right here for every panel. So it's going to always be, why are you not showing up that nice? It's always going to be the bottom segment here, right, for the panel. But I need 3 more, right? So I could do it the long way around, and I could say, okay, give me another list item, but this time give me index number 1, right? Like that. So it's going to give me the second curve. Again, we start counting from 0, right? So by default, the item index, which is it's getting for us, is index 0. So it's getting us the first item. And then the next item is going to be index 1. One after that is going to be index 2, and so on, right? So again, that counting from 0 type of a thing. And I could, kind of start copy pasting, and for this one, I could say 2, and so on. But that becomes a little bit clunky, and if we need a lot, let's say we need 12, that's going to be a very long, kind of set of nodes, and that's not that nice. So instead, what we can do, if we zoom into the list item node here and click on the plus sign here in the bottom, it will say +1, right? So whichever index you had, and by default it is 0, so it's the first item, this is going to be item plus 1, the next item on the list. And then I click it again, that's the next item in the list. And I click it again, that's the next item in the list, right? So we have 4 items. What happens if I click once more, right? There's no 5th item in the list. So at that point, it's a decision that Grasshopper needs to make, and actually that you make for Grasshopper. It's this input right here, which is called wrap. So if wrap is set to true, in a list of 4 items, the 5th one is going to be the first one, right? It's going to keep on going through the list. It's going to keep on repeating, right? So it's going to kind of count 0, 1, 2, 3, 0, 1, 2, 3, 0, 1, 2, 3, right? If wrap is set to false, the output here is going to be, I believe, null. It should be null, yes. Meaning that with that particular index, it couldn't get an item because there's only 4 of them in each list. So keep that in mind. That's how wrap works. If wrap is turned on, it will keep repeating. If wrap is turned the list, if wrap is turned off, it will kind of, once it reaches the end, it will just stop and start giving you errors and kind of complain a bit. Either way, we have 4 outputs here, we have 4 inputs here. Guess what we do? Straight up connect, 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 connect. And we have our surfaces, right? So now, what we have here is the frame, and is the surfaces within the frame, right? Corresponding to each panel. So if I use again the same tool called merge, there we go, and connect them together into one big happy family, and check the data tree. Ooh, okay, that's good. I hope that this is gonna happen. The data tree is going to look, it actually doesn't look that bad. What the heck? But either way, see how the addresses are all messed up and it's all weird? This happens when one of the inputs has not been simplified, right? So when it has redundant, unnecessary information in the addresses, then merge, as you plug both the frames and the panels into the merge, since I believe it was, yeah, so the frames have clean addresses, like 0, 1, 2, 3, 4, 5, for each panel, while the panels have not so clean addresses, 0.0, 1.0, 2.0. Those zeros here are unnecessary. They're just redundant. So when you give two data trees, even though they look exactly the same, 25 branches, 1 element in each branch, 25 branches, 1 element in each branch, even if you give 2 data trees to merge that look the same, but one of them has redundant information in the address, it's going to not merge properly, because what I wanted here to have after merge, it should be the same data tree structure, exactly the same, only it should have 2 elements, one for the frame and one for the inner glazing, right? The inner surface. So to fix that, I will just right click on the not so clean data tree here, output, surface, output, and I'll choose simplify. And suddenly it gets rid of unnecessary zeros here. Everything here gets merged properly. It has 2 elements, and that's it, right? So now if we look at this whole thing, right, it's not a big definition, but if we look at, the final output that we get from here, it's basically, we have 25 panels, and each panel has its own branch, its own data branch. And it's only, it's kind of everything that you do with that panel will be done in that separate branch. And in each of those branches lives two elements. And it's always going to be, the first element is always going to be the loft, right? So it's going to be the frame, while the second element is always going to be the inner surface. So at any point in time later on during your definition making, you will be able to exactly access the either the frame or the inner surface by just remembering how did you connect it to the merge here, right? How did you build the data tree? That's about it. There are quite a few, where is it, sets. So there are quite a few tools on how to deal with data trees right here. And it's under sets tree. So all of the tools are dealing with data trees are here. There are, for me, there are, let's see. So clean tree, graft tree, simplify tree, and flatten tree. These four are also located here. Flatten, graft, simplify. Oh wait, clean wasn't there. Yeah, okay, clean wasn't there. But flatten, graft, simplify are located here. What about flatten? So flatten is reverse of graft. If I were to, okay, I can show you here real quick. So we have a data tree with 25 branches, 2 elements in each branch. If I right click on the output here and choose flatten, data with 1 branch is 50 elements in that branch. So it takes all of the data in your data trees and it just starts cutting off the branches and just putting everything one after the other into one list. So you're getting rid of all of the data, like all of the information, what belongs to what. And then sometimes it's useful. Sometimes it's useful to just flatten everything out and work with everything as one list of things, right? And sometimes it's not. Right? So graft and flatten are two opposites to one another. And then simplify, I already talked about simplify. Reverse is basically, you have a list of items. I can show you. Series. Let's say you have a list of numbers, right? And let's just change it up 5. Let's say we start counting from 5 just so that it doesn't mess with your head, the fact that they will be the same with the item index. So you have a list of numbers, right? If I were to graft it, every number would receive its own branch, right? So we kind of covered that one. But there's also, ungraft, there's also an option to reverse the list. So what it's going to do, it's basically going to just flip it upside down. Things that were in the back are going to be in the top of the list. Things that were in the the top of the list will be in the bottom, right? So it's just kind of reversing the list. Sometimes useful. What's the difference between simplify, clean, and flatten tree? So simplify doesn't do anything with the data tree itself. It just removes unnecessary addresses, right? So you could, honestly, I think you could straight up use simplify on every single output of every single node, and it wouldn't make, it wouldn't break or make the definition. It's just basically, it removes all of the unnecessary bits from the actual address of the data tree. For instance, in Photoshop here, let me hide that, where we have had ducks, simplify would take care of a fact if, here I wrote 221. Here I wrote 221 as an address. So let me write it again, 221, right? So if I had an address of 00221, and then 00222, and so on, right? If I had this kind of address for these ducks, these zeros, they, as an address within the address, they make no difference, right? They're just there because of some sort of a redundant calculation or something like that within Grasshopper, right? So they're unnecessary. So simplify just basically finds which addresses are unnecessary, which parts of addresses are unnecessary, and just kind of gets rid of them. And then we have clean tree. So clean tree is kind of cool. I will not be showing an example of it, but just kind of explain real quickly what it does. So if we go to set tree, clean tree, basically you connect any data tree like so, to the tree input here, and then here you have toggles, yes or no, basically. These guys, and you connect them to these inputs: remove nulls, remove invalid, remove empty. So sometimes as you work with Grasshopper, you will have empty branches, right? Branches that just don't have anything in them. Maybe you don't need those empty branches anymore. Maybe you want to get rid of them, right? So then you can just say remove empty, toggle to yes, or to true, and then it's just going to kind of cut away that branch because it's empty, it's unnecessary. Remove invalid, it's basically if you have a mesh that's really messed up in one of your data branches, this will remove that branch with the really messed up mesh. And remove nulls, it's basically if you remove nulls and remove empty are quite similar to one another. It's just that remove empty usually, empty branches usually happen after you use some sort of a deleting algorithm. When you say that delete every third point in the list, right? And suddenly, some branches become empty. With remove nulls, usually nulls happen when you try to get something. For instance, where I showed you here with the list item, where we tried to get the fifth item of the list, but it didn't exist. So instead what Grasshopper gave us was null, There's also a third thing that is called NaN. N, small n, capital A, small n. That translates to not a number. And usually it happens when you just randomly try to do math with meshes or something like that and try to kind of connect things that shouldn't be connected. Then it's going to give you an error, this is not a number, stop. But that also registers as a null or an invalid object, I believe. So this is just straight up cleaning up the data tree physically, while the simplify cleans up the address of the data tree. Then we have tree statistics node. So if I connect my, let's connect it like so. The final result, right? Here from the tree statistics node, I have paths. Oh, and it's flattened, so I will unflatten it so that we actually have a tree. So we have paths, which is basically, it just gives us a list of all addresses of the data tree. Nothing fancy. Then length, it gives us how many elements there are in every branch as a number. And it gives us count, how many branches there are. So it's just basically extracting information that we already can see here with the Param Viewer, nothing more. That's tree statistics, quite useful, but depends on what you're doing. What else? Trim tree. Yeah, I can show you trim tree. So let's say we graft this. And then our data tree looks like, looks like that. 25 branches branching out into 2 branches, right? One branch for the frame, one branch for the panel for 25, one branch for the frame, one branch for the glazing for 25 panels, right? So it's 25 branches branching out into 2 branches each. What if you want to come back one step, right? What if you want to merge them back where frame and the glazing merge back into one branch, right? So you're just dealing with the panel and not these separate ones. You can't do flatten, because if you do flatten, then you get rid of all of the information, right? So it just becomes a list. But you still want to have those 25 branches. You just don't want to have that additional branching of frame and glazing. So to fix that, you can use trim tree. So even the name of it, reduce the complexity of a tree by merging the outermost branches. So basically what it says, it will take the glazing with the frame, and it's going to merge it into one branch. Glazing frame, one branch. Glazing frame, one branch, right? So we can do it like that. And then if I check it again, we're back to 25 branches, right? So it's imagine this, you have a tree and it has a bunch of branches at the end. All of those branches will be kind of merged back to where they start from, right? And you can say how many steps it should merge back. Usually like depth of 1 is the way to go. This one is a little bit more advanced, but I really use it quite a lot when I don't want to flatten the tree. Really quickly, let's just see if there's unflattened tree. Never used it, don't know how it works, so I won't explain it. And twine is actually the simplest way on how to show stuff. Let me just write cat, dog, mouse. Cat, dog, mouse. It can be more. Just like with list item, you can add more inputs, but it's basically cat, dog, mouse, and then the result is going to be a data tree with 3 branches, 1 element in each branch. Cat, dog, and mouse, right? So twine is basically you kind of create a data tree by yourself. Also somewhat useful. Next. That is not what I want. Explode tree is basically we can take any data tree and explode its branches as separate outputs. If that's what you want. So 0, 0 is going to be this panel right here. 0, 1, for some reason, why doesn't it give me 0, 1? Oh yeah, okay. So 0, 0 is this guy. 0, 1 is this guy, right? But what I can do is I can not graft it. And so branch 0 is this panel here, branch 1 is this panel here, branch 2 is this panel, and so on, right? So we can get any branch that we want. We can kind of explode the data tree. Besides that, there are two more that I want to show, and then we'll have a break. So there's flip matrix, and there is path mapper. So flip matrix, first of all, it just works with data trees that only have one locus point, meaning that if you have a data tree, come on, I'm just looking for one. There we go. If you have a data tree that looks like that, it's going to work, right? If you have a data tree that looks like grafted, that looks like that, or where's our Photoshop? If you have a data tree that looks like that, it's not going to work. That's because what it's going to do, what flip matrix does, it basically takes the first item of each list in a data tree, of each branch. It takes the first item and it puts all of them into one branch. And then it takes the second item and puts all in each list and each branch and puts them all into the second branch. And so on. So it kind of flips the logic of a data tree. And I can show you how it works this way. Let me not have this grafted. So now we have 25 branches here with 2 elements in each branch. If I run flip matrix on this, copy paste, and check it out, what I get from the flip matrix, I get data with 2 branches, so data tree with 2 branches with 25 elements in each branch. What happened here is all of the frames are now in one branch, in branch 0, and all of the glazing is in branch 1, right? So I can do bang, explodes tree, and now I have 2 outputs, and I can say custom preview, and let's just say framing gets a custom material and custom preview, swatch, glazing also gets a custom material, right? So here with flip matrix, we just took all of the frames and put them into one branch. And then we took all of the glazing panels and put them also in a separate branch, right? So instead of 25 branches with 2 elements in each branch, we get 2 branches with 25 elements in each branch. Quite a useful thing. Whew, last one. Okay. Here I'm not going to show you any examples, because this one is way too advanced, I think, for beginner level Grasshopper users. I struggle with this quite a bit when I need to use it in my daily work. But it's basically, here we have a mapping editor, right? And we can overwrite how we shuffle the branches. So it's basically this flip matrix, not just that, but think about it this way. It's flip matrix, only it's on really heavy steroids, right? So one of the ways would be, let me just connect it like so, create, let's say, renumber mapping. And let me double click that. So here I can, well, renumber is boring. Let's say create reverse mapping. Yeah, there we go. So this is address. this is item, list item, so item number. And this is same address, but item count -1 minus the list number, meaning it's going to be every list within every branch is going to be reversed by using this this node. Again, advanced stuff, unnecessary. Ew. Don't use that. At least for now. And that is it. Yeah, that's all I can show about data trees. Again, with data trees, you just need to kind of work with them until it starts working. And at a certain point, it's just going to click in your heads how it works. Takes a while, but that's how it is. I will be uploading this video to YouTube. So after a while, if you need to kind of check up on the data trees and how did they work? Remember the buckets and the ducks and the freckles and so on, and just open up the video and check it out. So I will stop the video here.